Welcome back everybody. In today's tutorial you are going to get a mini crash course in Actor-Critic methods in Tensorflow 2. We're going to have around 15 minutes of lecture followed by about 20 minutes of coding, and you're going to learn everything you need to know to go from start to finish with Actor-Critic methods. If you'd like to know more, you can always pick up one of my Udemy courses on sale right now, link in the description. Let's get started. Welcome to the crash course in Actor-Critic methods. I'm going to give a relatively quick overview of the fundamentals of reinforcement learning in general, and then of Actor-Critic methods in particular. Finally, we'll work together to code up our own Actor-Critic agent in Tensorflow 2. This is geared toward beginners, so feel free to ask some questions in the comment section. Reinforcement learning deals with agents acting on an environment, causing some change in that environment, and receiving a reward in the process. The goal of our agent is to maximize its total reward over time, even if it starts out knowing literally nothing about its environment. Fortunately, we have some really useful mathematics at our disposal, which makes figuring out how to beat the environment a difficult, yet solvable problem. The mathematics we're going to use relies on a very simple property of the system, the Markov property. When a system depends only on its previous state and the last action of the agent, we say it is Markovian. As we said earlier, the agent is given some reward for its action, so the set of states the agent sees, the actions it takes, and the rewards it receives forms our Markov decision process. Let's take a look at each of these components in turn. The states are just some convenient representation for the environment. So if we're talking about an agent trying to navigate a maze, the state is just the position of the agent within that maze. The state can be more abstract, like in the case of the lunar lander, where the state is an array of continuous numbers that describe the position of the lander, the velocity of the lander, its angle and angular velocity, as well as which legs are in contact with the ground. The main idea is that the state describes exactly what about the environment is changing at each time step. The rules that govern how the states change are called the dynamics of the environment. The actions are a little simpler to understand. In the case of a maze-running robot, the actions would be just move up, down, left, and right. Pretty straightforward. In the case of the lunar lander, the actions consist of doing nothing, firing the main engine, firing the left engine, and firing the right engine. In both these cases, the actions are discrete, meaning they're either one or the other. You can't simultaneously not fire the engine and fire the right thruster, for instance. This doesn't have to be the case, though. Actions can in fact be continuous, and there are numerous videos on this channel dealing with continuous action spaces. Check out my videos on soft Actor-Critic, deep deterministic policy gradients, and twin-delayed deep deterministic policy gradients. From the agent's perspective, it's seeing some set of states and trying to decide what to do. How is our agent to decide? The answer is something called the agent's policy. A policy is a mathematical function that takes states as inputs and returns probabilities as output. In particular, the policy assigns some probability to each action in the action space for each state. It can be deterministic, meaning the probability of selecting one of the actions is 1 and the others is 0, but in general, the probabilities will be somewhere between 0 and 1. The policy is typically denoted by the Greek letter pi, and learning to beat the environment is then a matter of finding the policy pi that maximizes the total return over time by increasing the chances of selecting the best actions and reducing the chances of selecting the wrong ones. The reward tells the agent exactly what is expected of it. These rewards can be either positive or negative, and the design of rewards is actually a tricky issue. Let's take the maze-running robot. If we give it a positive reward for exiting the maze, and no other reward, what is the consequence of that? The consequence is that the agent has no motivation to solve the maze quickly. It gets the same reward if it takes the minimum number of steps, or if it takes 100 times that number. We typically want to solve the maze as quickly as possible, so this simple reward scheme fails. In this example, we have to give a penalty or reward of -1 for each step and a reward of 0 for exiting the maze. Then the agent has a strong motivation to solve the maze in as few steps as possible. This is because the agent will be trying to maximize a negative reward, meaning get it as close to 0 as possible. So now that we have our basic definitions out of the way, we can start to think through the mathematics of the reinforcement learning problem. From the agent's perspective, it has no idea how its actions affect the environment, so we have to use a probability distribution to describe the dynamics. This probability distribution is denoted P of S prime and R given S and A, which just reads as the probability of ending up in state S prime and receiving reward R given we are in state S and take action A. In general, we won't know the value for this until we interact with the environment, and that's really part of solving reinforcement learning. Since we're dealing with probabilities, we have to start thinking in terms of expectation values. In general, the expectation value is calculated by taking into account all possible outcomes and multiplying the probability of that outcome by what you receive in that outcome. So in our Markov framework, the expected reward for a state and action pair is given by the expectation value of that reward, which is the sum over all possible rewards, the outcomes, multiplied by the sum over the probabilities of ending up in all possible resulting states. For a simple example, let's consider a simple coin toss game. If we flip a coin and it comes up heads, you get 1 point. If it comes up tails, you get -1 point. If we flip the coin 2 times, what is the expected number of points? It's the probability of getting heads multiplied by the reward for getting heads, plus the probability of getting tails multiplied by the reward for getting tails. So it's 0.5 times 1 plus 0.5 times -1. This gives an expected reward of 0 points, which is what you would intuitively expect. This is a trivial example, but I hope it illustrates the point. We have to consider all possible outcomes, their probabilities, and what we would expect to receive in each of those outcomes. When we go to put theory in practice, we're going to be doing it in systems that are what we call episodic. This means that the agent has some starting state, and there is some terminal state that causes the gameplay to end. Of course, we can start over again with a new episode, but the agent takes no actions in this terminal step, and thus no future rewards follow. In this case, we're dealing with not just individual rewards, but with a sequence of rewards over the course of that episode. We call the cumulative reward the return, and it's usually denoted by the letter G. Now, this discussion is for games that are broken into episodes, but it would be nice if we could use the same mathematics for tasks that don't have a natural end. If we have a game that goes on, then the total sum of rewards will approach infinity. It's absurd to talk about maximizing total rewards in an environment where you can expect an infinite reward, so we have to do a little modification to our expression for the returns. We need to introduce the concept of discounting. We're going to reduce the contribution of each reward to the sum based on how far away in time it is from our current time step. We're going to use a power law to describe this reduction so that the reward gets reduced by some additional power of a new hyperparameter we'll denote as gamma. Gamma is between 0 and 1, so each time we increase the power, the contribution is reduced. If we introduce gamma into the expression for the return at time step t, we get that the return is just the sum over k of gamma to the k multiplied by the rewards at time t plus 1 plus k. Besides being a trick to make sure we can use the same mathematics for episodic and continuing tasks, discounting has a reasonable basis in first principles. Since our state transitions are defined in terms of unknown probabilities, we can't really say how certain each of those rewards were. States that we encounter further out in time become less and less certain, and so the rewards for reaching those states are also less and less certain. Thus, we shouldn't weight them as much as the reward we just received. If you've been following along carefully, something may not quite add up here. All of this math is for systems with a Markov property, which means that they depend only on the previous state in action. So why do we want to keep track of the entire history of rewards received? Well, it turns out that we don't have to. If you do some factoring in the expression for the return at time step t, you find that the return at time t is just the sum of the reward at time t plus 1 and the discounted return for the t plus 1 time step. This is a recursive relationship between returns at each time step. It's more consistent with the principles of the Markov decision process, where we're just concerned with successive time steps. Now that we know exactly what the agent wants to maximize, the total returns, and then function for how it's going to act, the policy, we can actually start to make useful mathematical predictions. One quantity of particular interest is called the value function. It depends on the agent's policy pi and the current state of the environment, and gives us the expectation value of the agent's returns starting from time t in state s, assuming it follows the policy pi. There's a comparable function for the value of state and action pairs, which tells us the value of taking action A in state S and then following the policy pi afterwards. It's called the action value function and is represented by the letter Q. So how are these values calculated in practice? Well, in reality, we don't solve these equations, we estimate them. We can use neural networks to approximate the value or action value function because neural networks are universal function approximators. We sample rewards from the environment and use those to update the weights of our network to improve our estimate for the value or action value function. Estimating the value function is important because it tells us the value of the current state and the value of any other state the agent may encounter. Solving the reinforcement learning problem then becomes an issue of constructing a policy that allows the agent to seek out the most profitable states. The policy that yields the best value function for all states in the state space is called the optimal policy. In reality, it can be a set of policies and they're all effectively equivalent. Various schemes to find these optimal policies exist, and one such scheme is called the Actor-Critic method. In Actor-Critic methods, we're using two deep neural networks. One of them is used to approximate the agent's policy directly, which we can do because it's just a mathematical function. Recall that the policy is just a probability distribution over the set of actions, where we take a state as input and output a probability of selecting each action. The other network, called the critic, is used to approximate the value function. The critic acts just like any other critic, telling the actor how good each action is based on whether or not the resulting state is valuable. The two networks work together to find out how best to act in the environment. The actor selects actions, the critic evaluates the states, and then the result is compared to the rewards from the environment. Over time, the critic becomes more accurate at estimating the values of states, which allows the actor to select the actions that lead to those states. From a practical perspective, we're going to be updating the weights of our deep neural network at each time step because actor-critic methods belong to a class of algorithms called temporal difference learning. This is just a fancy way of saying that we're going to be estimating the difference in values of successive states, meaning states that are one time step apart, hence temporal difference. Just like with any deep learning problem, we're going to be calculating cost functions. In particular, we're going to have two cost functions, one for updating our critic and the other for updating our actor. To calculate our costs, we want to generate a quantity we'll call delta, and it's just given by the sum of the current reward and the discounted estimate of the new state, and then subtracting off the value of the current state. Keep in mind that the value of the terminal state is identically 0, so we need a way to take this into account. The cost for the critic is going to be delta squared, which is kind of like a typical linear regression problem. The cost for our actor is a little more complex. We're going to multiply this delta by the log of the policy for the current state and action the agent took. The reason behind this is a little complex and is something I go into more detail about in my course, or you can look for it in the chapter on policy gradient methods in the free textbook by Sutton and Bardo. So let's talk implementation details. We're going to implement the following algorithm. Initialize a deep neural network to model the actor and critic. Repeat for a large number of episodes. Reset the score, terminal flag, and environment. While the state is not terminal, select an action based on the current state of the environment. Take the action and receive the new state, reward, and terminal flag from the environment. Calculate delta and use it to update the actor and critic networks. Set the current state to the new state and increment the episode reward by the score. After all the episodes have finished, plot the trend in scores to look for evidence of learning. There should be an overall increase in score over time. You will see lots of oscillations because actor-critic methods aren't really stable, but the overall trend should be upward. Another thing you may see is that the score can go upward for a while and then fall off a cliff. This isn't uncommon because actor-critic methods are quite brittle and they're really not the best solution for all cases, but they are a stepping stone to more advanced algorithms. Other important implementation details. You can use a single network for both the actor and critic. So you'll have common input layers and two outputs, one for the actor and one for the critic. This has the benefit that we don't have to train two different networks to understand the environment. You can definitely use an independent actor and critic, it just makes the learning more difficult for an algorithm that is already pretty finicky. We'll let it play almost 2,000 games with a relatively large deep neural network, something like about 1,000 units in the first hidden layer and 500 units in the second. The hard part is going to be the actor. As I said earlier, the actor models the policy, which is a probability distribution. The actor layer will have as many outputs as there are actions, and we use a softmax activation because we're modeling probabilities, and they had better sum to 1. When selecting actions, we're going to be dealing with discrete action spaces, so this is what is called a categorical distribution. We're going to want to use the Tensorflow _probability package for the categorical distribution, and then use the probabilities generated by the actor layer to get this distribution, which we can then sample and use the built-in logprob function for our cost function. As far as the structure of our code, we're going to have a class for our actor-critic network, and that will live in its own file. We'll also have a class for our agent, and that will have the functionality to choose actions, save models, and learn from its experience. That goes in a separate file. The main loop is pretty straightforward, but it does go in its own file as well. Okay, now that we have all the details out of the way, let's go ahead and get started coding this. So now that we have all of our lectures out of the way, we're going to go ahead and proceed with the coding. We're going to start with the networks. We begin as always with our imports. So we will need OS to handle file joining operations for model checkpointing. We will need Keras. And we will need our layers, which for this example is just going to be a dense layer. So we will have our Actor-Critic network. And you see a case of converging engineering here where TensorFlow and PyTorch both have you derive your model class from the base model class. And we can go ahead and define our constructor. That will take a number of actions as input. The number of dimensions for the first fully connected layer, we will default that to 1024. And for the second, we will default it to 512. We will have a name for model checkpointing purposes and a checkpoint directory. Very important, you must remember to do a make directory on this temp/Actor-Critic before you attempt to save a model, otherwise you're going to get an error. The first thing you want to do is call your superconstructor, and then go ahead and start saving your parameters. Now, also very important for our class that we've derived from the base class, in this case the Actor-Critic network class, we have to use model name instead of name because name is reserved by the base class. So just be aware of that, not a huge deal. Checkpoint directory. And then we'll have our file. And that will be os path join, the directory name plus underscore AC. I like to use underscore algorithm, in this case AC for Actor-Critic, in case you have one directory that you use for many different algorithms. If you're just using, like, say, a working directory, you don't want to confuse the model types. Otherwise, if you have a good model saved, you don't want to override it with something else. Now we'll go ahead and define our layers. And that will be fully connected dense layers. The neat thing about Keras is that the number of input dimensions are inferred, so we don't have to specify it. That's why we don't have an input dims for our constructor. And it will output FC1 dims with an activation of ReLU. FC2 will be similar. And then we will have two separate outputs. So we have two common layers and then two independent outputs. One for the value function, and that is single valued with no activation. And the second is our policy pi, and that will output an actions with a softmax activation. Recall that the policy is just a probability distribution, so it assigns a probability to each action, and those probabilities have to add up to 1 because that's kind of what probabilities do, right? Next, we have to define our call function. This is really the feed forward, if you're familiar with that from PyTorch. So we'll just use some generic name like value, doesn't really matter, and pass it through the second fully connected layer, and then get our value function and our policy pi, and then return both the value function and the policy pi. So that is really it for the Actor-Critic network. All of the interesting functionality happens in the agent class. So let's go ahead and start writing the agent class. So we begin as always with our imports. we will need Tensorflow. We will need our optimizers. In this case, we're going to use an atom optimizer, probability. We will need TensorFlow probability to handle our categorical distribution to model our policy directly. You have to do a pip install TensorFlow probability before you can run this. This is a separate package from TensorFlow. And we will also need our Actor-Critic network. So let's go ahead and code up our agent. So our initializer is pretty straightforward. We will need some default learning rate. I'm going to use 0003. It doesn't really matter. I'm going to pass in a specific learning rate in the main file. We will have a gamma of 0.99 and default in actions of some number like, say, 2. So we're going to go ahead and save our parameters. Recall that gamma is our discount factor. We're going to need a variable to keep track of the last action we took. This will be a little bit more clear when we get to the learn function. And it has to do with the way we calculate the loss, because we have to use a gradient tape for TensorFlow 2. It's just a bit of a workaround for how TensorFlow 2 does things. We need our action space for random action selection. That's just a list of actions from 0 to n actions -1. We need our Actor-Critic. Want to make sure to specify the number of actions, and we want to compile that model. So Actor-Critic compile with an atom optimizer and learning rate defined by alpha. Next, we have the most basic functionality of our agent, the functionality to choose an action. And that takes the current state of the environment as input, which we have to convert to a tensor. And in particular, we have to add an extra dimension, batch dimension. The reason being that the deep neural network expects a batch of inputs, and so you have to have something other than a 1D array. It has to be 2-dimensional. So we just add an extra dimension along the 0th dimension. So then we will feed that through our deep neural network. We don't care about the value of the state for the purpose of choosing that action, so we just use a blank. And we will get the probabilities by passing the state through the Actor-Critic network. And then we can use that output, the probabilities defined by our neural network, to feed into the actual TensorFlow probabilities categorical distribution, and then use that to select an action by sampling that distribution and getting a log probability of selecting that sample. Sorry, that's TFP. Categorical and probabilities given by probs. And our actual action will be a sample of that distribution. And we don't actually need the log prob at this stage. We will need the log prob when we calculate the loss function for our deep neural network, but we don't need it now, and it doesn't make sense, or rather it doesn't actually work to save it to a list, let's say for use later here, because this calculation takes place outside of the gradient tape. TensorFlow 2 has this construct of the gradient tape. It's pretty cool. It allows you to calculate gradients manually, which is really what we want to do here. But anything outside of that tape doesn't get added to the calculation for backpropagation. So the log prob doesn't matter at this point, so why bother calculating it? One thing we do need, however, is the action that we selected. So we will save that in the action variable, and we will return a NumPy version of our action, because action is a TensorFlow tensor, which is incompatible with the OpenAI Gym. It does, however, take NumPy arrays, and we want the 0th element of that because we added in a batch dimension for compatibility with our deep neural network. And a little bit confusing, but that is what we have to deal with. Next, let's do a couple of bookkeeping functions to save and load models. Those don't take any inputs. And so it will save the weights of the network to the checkpoint file. We do the inverse operation to load models. And we will load weights from a checkpoint file. So that is it for the basic bookkeeping operations. Next we have the real heart of the problem, the functionality to learn. So this will take a number of inputs. It'll take the state, reward received, new state, and terminal flag as input. The first thing we want to do is convert each of those to TensorFlow tensors. And make sure to add a batch dimension. And I like to be really pedantic with my data type, so I will cast it to TF float 32. And we don't have to add a batch dimension to the reward because it is not fed to a deep neural network. So now we get to calculate our actual gradients using something called the gradient tape. And we'll set persistent to true. I'm not actually sure that's needed. I'm going to go ahead and experiment with that when we go ahead and run the code. But I have it that way. I might have just copied and pasted code from somewhere else, so let me double check. But we want to feed our state and new state through the Actor-Critic network and get back our quantities of interest. So we feed the current state and then the new state, but for the new state, we don't care about the probabilities. We just care about the value. And that is for calculation of our delta. But for the calculation of our loss, we have to get rid of that batch dimension. So we have to squeeze these two parameters. And the reason you have to do that is because the loss works best if it's on a one-dimensional quantity, or rather a scalar value rather than a scalar value inside of brackets. So it has to be a scalar instead of a vector containing a single item. It's just something we have to do. I encourage you to play around with it to double check me on that. I move between distributions, frameworks, so sometimes stuff isn't always 100% necessary, even if it doesn't hurt anything. So we need our action probabilities for the calculation of the log prob. TFP distributions categorical. And we define our probs by the output of our deep neural network. And then our log prob is action probs.log prob of the self.action. And this is the action that we saved up at the top when we calculate the action for the agent. So this is the most recent action. Then we calculate our delta. That is reward plus gamma multiplied by the value of the new state times 1 minus int of done. And the reason for that is that the value of the terminal state is identically 0 because no returns, no rewards follow the terminal state, so it has no future value. And subtract off the state value. So our actor loss is minus log prob times that delta, and the critic loss is delta squared, and the total loss equals actor loss plus critic loss. And then we can go ahead and calculate our gradients. So our gradient is tape.gradient total loss with respect to the trainable variables. optimizer apply gradients, and this expects a zip as input. So we're going to zip the gradient and the trainable variables. All right, and that is it for the Actor-Critic functionality. So I'm going to come back to this in a few minutes to see if I need that persistent. I don't believe I do. I believe I need this in the case when we have, if we were to have, say, separate actor and critic networks and had to calculate gradients with respect to two separate sets of trainable variables. I believe that's when the persistent equals true would be necessary. And when we had coupling between the loss of one network and the other, it's so that it keeps track of the gradients after it does the back propagation, kind of like in PyTorch where it throws it away and you have to tell it to retain the graph. I'll double check on that though. So let's go ahead and write and quit, and then we're ready to go ahead and code up our main file. So with our imports, we will need gym, we will need numpy, we will need our agent, we will need our plot learning curve function. I'm not going to go into any detail on this. It's just a function to plot data using matplotlib with some labeled axes. It's nothing really worth going into. First thing we'll do is make our environment. And I'm using the cart poll because it runs very quickly, and the Actor-Critic method is quite brittle, quite finicky. You will observe in many cases where it will achieve a pretty decent score and then fall off a cliff because the learning rate was just a little bit too high. So there are a number of problems with the algorithm, and it's easiest to test in a very simple environment. In my course, we used the lunar lander environment, and I did more hyperparameter tuning to get it to actually get pretty close to beating the environment, I believe. In this case, we won't quite beat it. We achieve a high score of like 140 points or so, when beating it is 200. But I leave the exercise of hyperparameter tuning to you, the viewer. I gotta leave something for you to do as well, right? So we'll define our agent with a learning rate of 1 by 10 to the minus 5 and a number of actions defined by our environment action space underscore n. Then we'll have, say, 1800 games, about 2000, with a file name of cartpoll.png. I would encourage you, if you do hyperparameter testing, to put the string representations of those hyperparameters here in the file name, so that way when you look at it later you don't get confused and you know what hyperparameters were used to generate which plot. So our figure file is just plots plus the file name. I split it up, you don't have to do it that way. We want to keep track of the best score received, and it'll default to the lowest range, so that way the first score you get is better than the lowest of the range, and so you save your models right away. An empty list to keep track of the score history, a boolean for whether or not we want to load a checkpoint. So if we're going to load a checkpoint, then we want to load models. And then finally we want to go ahead and start playing our games. We want to reset our environment, reset our terminal flag, set our score to 0. And while we're not done with the episode, we can choose an action. Get the new state, reward, done, and info from the environment. Increment our score. If we're not loading a checkpoint, then we want to learn. Either way, we want to set the current state to the new state. Otherwise, you will be constantly choosing an action based on the initial state of the environment, which obviously will not work. You also want to append the score to the score history for plotting purposes and calculate a score, an average score of the previous, I don't know, say 100 games. And if that average score is better than your best score, then set the best score to the average score. And if we're not loading a checkpoint, then save your models. So this inner conditional statement keeps you from overriding your models that had your best scores when you're actually testing. If you just saved the model every time, then you'd be overriding your best model with whatever, which may not be the best model. So at the end, if we're not loading a checkpoint, actually we can just plot either way. Let's do that. It's got our x-axis and plot learning curve x score figure file. Okay, now I have to do a make dir on plots temp. Did I call it temp / Actor-Critic? Otherwise this stuff won't work. And you also want to do a pip install flow TensorFlow probability, because that is a separate package. Of course, I already have it. So let's go ahead and try to run this and see if I made any typos. I'm almost certain I did. So it says something is not callable. Oh, that's because I have forgotten my multiplication sign. So that is in line 49. Yeah, it thinks I'm trying to call something here when I really want to multiply. Oh, you know what I did forget? One thing I did forget, of course, is down here I forgot my debug statement. So let's do this. That's pretty funny. Episode I score %1f always have to forget something, of course. Okay, there we go. So one other thing I want to do is come back here to Actor-Critic and get rid of this persistent equals true. I don't think I actually need this. Sometimes I just copy and paste code, and then as I'm doing the video I realize, oh hey, I don't always need all of that stuff. Okay, so yeah, it does run. Alrighty, so I'm gonna go ahead and switch over to another window where I have let this finish up because there's no point letting it run for another 1800 games. So let's go ahead and check that out. So here you can see the output of the other 1800 games I ran, and it does achieve a score of around 167, 168, about 170 points or so, which is almost beating the environment. It's pretty close. If you take a look at the learning plot here, you can see that it has an overall upward trend and it's linear. And the reason I don't let it continue is because, as I alluded to in the lecture, these models are very brittle, and so sometimes you can get on a very narrow slice of parameter space where your model is doing well, and any small step out of that range blows up the model. One thing to fix that is replay memory. Allows you to get a broader sampling of experiences and get a little bit more stable learning, but that doesn't work by bolting it directly onto Actor-Critic methods. At least from my experience, I've tried it. I have a video on that. I wasn't able to get it to work. Maybe some of you can. That would be fantastic if you could, but in my case, I didn't get it to work. I thought it would work. It does not. And in fact, there's a whole separate algorithm called Actor-Critic with experience replay that deals with bolting experience replay onto vanilla Actor-Critic methods. So I hope this was helpful. It's pretty hard to give a really solid overview in like a 30-40 minute YouTube video, but it serves to illustrate some of the finer points of actor-critic methods and some of the foundational points of deep reinforcement learning in general. In my courses, I go into much more depth, and in particular, I show you how to actually read papers, how to turn papers into code. A useful skill that's really hard to find anywhere else on YouTube or Udemy. So if you like the content, make sure to leave a like, subscribe if you haven't already, and leave a comment down below with any questions, comments, criticisms, concerns, and I will see you in the next video. Oh, really quick, before we do, let's check in on the other terminal to make sure it's actually learning. So here is the output, and you can see as it's going along, it is saving some models, and the score is generally trending upward over time. And that's why you get the saving models, because the score is best than the last best score. So we didn't make any fundamental errors in our code. If it doesn't achieve the same result, that isn't entirely surprising, because there is a significant amount of run-to-run variation. The code is functional. It's up on my GitHub. If you want to go ahead, check it out. I'll leave a link in the description. See you in the next one.